Alright, this is homework for Chapter 6. I have information in a compact disk is stored in pits whose depth is essentially 1/4 the wavelength of the laser light used to read the information. The wavelength in air is 780 nanometers, but the wavelength on which the pit depth is based is measured in the plastic. That has an index of 1.55 that makes up most of the disk. Find the pit depth. So really what we need to find here is the wavelength of the light. And when light enters a medium, let's say that this is air and this is our plastic, my wavelength is actually going to decrease. So here it is in air. And now my wavelength has gotten smaller. This is my wavelength in air, and that's my wavelength in the plastic. The wavelength actually gets smaller. It travels at a slower speed in a medium, but it has the same frequency. So the distance between the peaks has to decrease if it has the same frequency. Anyway, the point is the wavelength gets smaller. And we can calculate this because the index is proportional to the wavelength in this way, n1 lambda 1. So if n gets bigger, lambda goes down. If n increases, the wavelength decreases. And so n1 lambda 1 is equal to n2 lambda 2 in this way. So we're looking, I'll call this lambda 1, I'll call this lambda 2. We're looking for lambda 2. So that's going to be n1 lambda 1 over n2. Now we can put in some numbers here. N1, that's the index in air, is just 1 times 780 nanometers, that's the wavelength in air, divided by 1.55. So that gives us the wavelength in the plastic, which is 503 nanometers. And now we want to know the height of the pit, or the depth of the pit, and we're told that it's 1/4 of the wavelength. So that's 503 over 4. And that gives me 126 nanometers. That's the answer. All right, light is incident on a set of mirrors that are at a right angle to one another. The initial angle of incidence, theta 1, is 30 degrees with respect to the first mirror. So this angle is 30 degrees. Now I want to know what are the incident and reflected angles of the light ray on the second mirror and how high up does the ray strike the second mirror. All right, this isn't really drawn to scale. That angle looks more like 40 or 45 degrees. But if I draw the reflected ray, I know that this angle has to be 30 degrees, and so this angle has to be 60 degrees. If that angle is 60 degrees, then this angle is 30 degrees, and then the new incident angle is going to be 60 degrees. So the reflected ray over here is also going to be at 60 degrees. So that is part A. The incident and the reflected angles are both 60 degrees. And I also want to know how high up does the ray strike the second mirror. So I want to know what is this distance. I'll call it y for part B. Well, the tangent of 60 is opposite over adjacent. That's going to be y divided by 1.30. If I solve that for y, I find that y is equal to 2.25 meters. That's the answer to part B. This figure shows an overhead view of the corridor with a plane mirror M mounted on one end. A burglar B sneaks along the corridor directly towards the center of the mirror. If D equals 5 meters, how far from the mirror will the burglar be when the security guard S can first see her in the mirror? Okay, the burglar, when the security guard first sees the burglar, light rays from the burglar are going to come to the security guard from the very edge of the mirror. Okay. So I want to find where is the position of the burglar so that light rays from that mirror will come to the security guard just from the very edge of it. So because of these sides, I know that this angle is 45 degrees. And so my reflected angle is going to be 45, and so my incident angle will also be 45 degrees. All right, that means that my burglar has to be right here. So I'm going to draw this triangle right here. I know that this angle is 45, and so this angle is also 45. I know that this distance is d over 2, which is equal to 2.5 meters. And since this is an equilateral isosceles triangle, that is that this side equals this side, this distance is also 2.5 meters. So the burglar is going to be 2.5 meters, 2.5 meters from the mirror. So actually, the security guard will see the burglar before the security guard will see the burglar in the mirror. So you actually see the burglar in real life before you see it before you see that person in the mirror. Let's sort of blow this up a little bit. Let's see if I can erase this, because this doesn't really make much sense, right? Like logically, it doesn't make a lot of sense. But let me show you the ray diagram. Blow this up. All right. Let's imagine first that the burglar is back here. All right. I'm going to have a ray that comes to the mirror right there. And I know that this angle has to equal that angle. See, so that ray doesn't go to the security guard. That's with the burglar further back. Well, you say, well, maybe a different part of the mirror. So let's say, instead, I have a ray that comes here. Look, this ray goes even further away from the security guard. So there's no rays that actually reach the security guard when the burglar is back at that point. So now let's consider the burglar is right here, which is where we know, just from that calculation, where we know that the security guard will actually see the burglar. So I'm going to draw a ray, the furthest edge. I know that this angle has to equal this angle. See, it goes right to the security guard. All right, we can also take it further back. So now let's say, instead of being there, let's say that the burglar, let's say the burglar's right here. Ray goes there, nowhere near the security guard. You can try this at home. Just look at a mirror on your wall and stand to the side of it like the security guard is here, and you'll see that you're not able to see objects that are right in front of the mirror until they get to a certain position. All right, let's go on to the next one. You shine a laser through water whose index is 1.3, as in this figure. The laser beam leaves the water, travels in air, and strikes a wall at some distance y from the floor. What is the height y? Let's just sketch this out first. I have this laser light. It leaves here. It's going from a high index to a low index of refraction. So it's going to bend away from the normal. So it turns out that our scale here is not exactly right. It's actually going to come to right about there. Now, I want to figure out what are the various angles and distances that I'll need. So first, let's just find out what is the refracted angle. I know that this angle has to be 30 degrees. That's 90 minus 60, which is 30. Now let's calculate what is this angle, and I'll call this, let's call it theta 2. All right, so I have n1 sine theta 1 equals n2 sine theta 2. N1 is, was it 1.3 sine of 30? Equals 1 sine of theta 2. And then I solve for theta 2. And theta 2 is going to equal 41 degrees. All right, so this angle is 41 degrees. Now, I need to find out a couple of things. I really need to know what is this height. All right, in order to find that, I'll need to know this angle, which I'm going to go ahead and label. It's just 90 minus 41, so that's 49 degrees. And then I'll also need to know what is this side, so that I can use the tangent of 49 as opposite over adjacent to get this red side, which is labeled right here. All right, so I need to find the adjacent side to that 49-degree angle. In order to find that, I need to find what is this side right here. All right, so this side, I can say, let's see, the tangent of 60 is opposite over adjacent. That's going to be 0.75 over x. And then I can solve that for x and find that x is 0.43 meters. All right, if that's 0.43 meters, and this distance is 1.30 minus 0.43, and that is equal to 0.87 meters. So I have 0.87 meters here. Now, I can find this side. I can say that the tangent of 49 is equal to opposite over adjacent. I'm going to call this, I'll call it y2, over adjacent, which is 0.87. And then y2 is equal to tan of 49 times 0.87, which is 1 meter. All right, now I want to know the total height. That is this total distance right here. And y is going to equal y1 plus y2, where I'm letting this value be y1. So that's 0.750 plus 1 meter, which is 1.75 meters. And that's the answer. A lot of geometry, trigonometry, figuring out various angles and sides, but that's really what a lot of optics is geometry. And with a little bit of Snell's law or the law of refraction thrown in here to find the angle of refraction. Light is incident on a normal to a 1 centimeter layer of water that lies on top of a flat lucite plate with a thickness of 0.5 centimeters. How much more time is required for light to pass through this double layer than is required to travel the same distance in air? And there's the index for lucite. All right, so this is what I have. I have a 1 centimeter layer of water. This distance is 1 centimeter. And then I have an additional layer, which is a half a centimeter of lucite. So this is H2O, and this is lucite. And then I have light that's traveling through both of these layers. In addition to this, I have light that's traveling through air, the same height. So this is a distance of 1.5 centimeters. I want to compare the times to travel through these. Right. I know that the light travels slower in a higher index of refraction. That speed is given as the speed of light over the index of refraction. Now in air, n is equal to 1. So the speed in air is equal to c, which is equal to 3 times 10 to the 8th. Let's go ahead and calculate the time required to travel in air. The time in air is just the distance over the speed. That's going to be 0.015 meters divided by 3 times 10 to the 8th meters per second, which is the speed of light. And that gives me 5 times 10 to the minus 11 seconds. Over here, however, my light is traveling slower by the factor n. N for water was 1.3, and N for lucite is 1.59. Alright, so I can do the time for water is distance over velocity, or distance over speed. So that's going to be 0.01 meters, that's my distance, divided by my speed. And here I'm going to substitute this in. So it's going to be 3 times 10 to the 8th divided by 1.3. And that gives me the time in water, which is 4.3 times 10 to the minus 11. And then, in a similar way, I can do the time for lucite, which is 0.005 meters, divided by 3 times 10 to the 8th, over 1.59. And that gives me the time for lucite, which is 2.65, I'll just call it 2.7, times 10 to the minus 11 seconds. Now, to get the total time, I just add these two up. So that's what, 6, 7 times 10 to the minus 11 seconds. So the change, or the difference in these two times, 7 minus 5 times 10 to the minus 11 is 2. Requires that much more additional time to travel through the lucite water interfaces than it does just in air. This is a very small time, so it's actually a pretty effective timing device for getting very small measurements of time, differences in time. All right, a ray of light strikes a flat 2 centimeter thick block of glass at an angle of 30 degrees with a normal. Trace the light beam through the glass and find the angles of incidence and refraction at each surface. Let's blow this up just a little bit. So I have this light ray that comes in. It's going to bend towards the normal first, and then it's going to bend away from the normal. Now, we've already said in class that this angle, if I'm coming back into the same medium, should be the same as my original incident angle, so 30 degrees. But we'll show that. Alright, I can say, I'll call this N1 and this N2. I can say N1 sine theta 1 equals N2 sine theta 2. So N1 is equal to 1 sine of 30 equals N2, which is 1.5 times sine of theta 2. Solving that for theta 2, I find it to be 19.5 degrees. I'll just call it 20 degrees. All right, so this angle right here is 20 degrees. Likewise, this angle is 20 degrees. And now you should also be able to see that this angle should be 30, because if I just sort of do the backwards, I'm going to write this, although it's a little redundant. I can say 1.5 sine of 20 equals 1 sine of theta. Look, that's the same thing that I wrote up here. It's just backwards. And so theta equals 30 degrees. The index of refraction for red light and water is 1.331, and that for blue light is 1.34. If a ray of white light enters the water at an angle of incidence of 83 degrees, what are the underwater angles of refraction for the blue and red components of the light? All right, so I have light that comes in. This angle, 83 degrees. The blue light has a higher index of refraction, so it's going to be refracted more. So my blue light is going to look like this. The red light, which has a lower index of refraction, well, not quite that much, it's going to be refracted less, like that. So my red and my blue light are going to be split because of this difference in their indices of refraction. So now let's just calculate what those two angles are. That is, first we'll do what is this blue angle, the angle for the blue light. I have 1 as N1 sine theta 1 equals N2 sine theta 2. Looking for theta 2. 1 sine of 83 equals the index for blue light, which is 1.34, sine of theta 2. And then I solve that for theta 2, which is 47.79 degrees. Now I can do the same thing for red. 1 sine of 83. The index for red light was 1.331. And theta for the red light is 48.22 degrees. So this angle is 48.22, and this angle is 47.79. So I've split that light into its different colors, into its different wavelengths. Certain kind of glass has an index of refraction, 1.65 for blue light, a different index for red light. Beam containing these two colors is incident at an angle of 30 degrees. What is the angle between the two beams inside the glass? All right, well, this is exactly the same. Basically the same. So for blue light, I have, well, let's draw the picture first. I have light incoming at 30 degrees. My blue light is going to be refracted more because of its greater index of refraction. My red light will be refracted less because of its lower index of refraction. And now I want to know what is this angle, the difference between the two angles. So just like I did before, blue light is going to be N1 sine theta 1 equals N2 sine theta 2. That's 1 sine of 30 equals 1.65 sine of theta 2. And then my theta 2 is going to equal 17.6. And then for red light, I have a similar thing. 1 sine of 30 equals 1.615 sine of theta 2. Solve for theta 2. I get 18 degrees. So this angle, I'm going to call it delta theta, is the difference between those two is 0.4 degrees, a small but measurable angle. This figure represents a simplistic optical fiber. I have a plastic core surrounded by a plastic cladding. Notice that the cladding has a lower index of refraction than the core. So this is 1.4 and this is 1.45. Out here we have n equal to 1. And I'll call this n0. I want to know what is the maximum value of theta naught, this angle right here, that will give us total internal reflection. Right, the light has to enter the core at a particular angle in order for it to not leave the fiber optic cable, and I want to know what that is. So the first thing I need to do is find out what is this critical angle called theta c. All right, so I use the law of refraction. N1 sine of theta c equals N2 sine of 90 degrees. Remember, total internal reflection is just a special case of the law of refraction where the refracted angle is 90 degrees. So it's like this light comes up and it never actually leaves the core. It travels at 90 degrees. Now it's not drawn here in that way because actually as that critical angle gets bigger, that light reflects back into the core. It doesn't just travel along the edges. But we're looking for the maximum value of theta naught. So we want to know what is the minimum value of theta c, the critical angle. All right, so we have 1.45 sine of theta c equals 1.4 Sine of 90, of course sine of 90 is 1. I solve this for theta c, it's the inverse sine of 1.4 over 1.45. And that gives me my critical angle to 75 degrees. Now, if that angle is 75 degrees, this angle has to be 75 minus 90, or 15 degrees. And now I want to know theta naught. So this is a more typical use of the law of refraction. N0 sine of theta 0 equals N1 sine of theta 1. That is 1 sine of theta naught equals 1.45 sine of 15. And I can solve this for theta naught. It's the inverse sine of 1.45 sine of 15, which is 22 degrees. And that's the final answer. If that angle gets bigger, that is, let's say that this is 22, but what if the light comes in at a steeper angle, then it would refract like that, and then it would fract out of the fiber optic cable. So that is the maximum value.